So, here is a cyclohexane example. So, we are looking at 1,2 disubstitution in the case of cyclohexane. So, in the cyclohexane 1,2 position there is an axial bond, there is an equatorial bond. So, in the conformation analysis we will be studying in detail about how these bonds are represented. Here we will only be looking at the cis trans isomerism. So, one bond is pointing upwards and this bond is also pointing upwards. So, when two bonds are pointing upwards we call, because these are in the same side, that is up. So, this is called cis arrangement, and when we go to this representation, here one of the bond is pointing upwards, another bond is pointing downwards. So, these are in the opposite direction. So, this is called trans arrangement. So, in the 1,2 disubstitution, axial equatorial bonds on adjacent carbons are up or cis arrangement, and in the case of again cyclohexane, axial bonds, or we can also say equatorial bonds. So, these two combinations both are 1,2 or trans. And if we go to the 1,3 disubstitution, so here again the first bond, that is the bond number 1, axial bond is pointing upwards, and the third one again the axial bond is pointing upwards. So, we have the two bonds pointing upwards, that means on the same side. So, when it is the same side we call this as a cis arrangement, and when we go to the axial bond, this is pointing up, the equatorial bond, this is pointing down. So, this axial equatorial arrangement in 1,3 disubstitution is called trans arrangement. And when we go to the 1,4 disubstitution, here the axial bond at position number 1 and the equatorial bond at position number 4 both are pointing in the same side up, and this is on the same side. So, this is called cis arrangement, and the first carbon axial bond and the fourth carbon equatorial bond are pointing opposite sides. So, this is a trans arrangement. Similarly, we can also use the equatorial arrangement. So, the 1,4 di-equatorial arrangement is also a trans. 1,4 axial arrangement is also trans. So, these are one and the same, and in the case of equatorial and axial, this is cis arrangement. Similarly, if you go with the other one, this is also cis arrangement. So, this way we can actually represent the cis and trans arrangements in cyclic systems. Let us look at cis trans isomers across double bonds. So, in the case of terminal alkenes, when two atoms are similar, two hydrogen atoms are present, we do not have any cis trans isomerism. Why? Because we have already seen, for showing cis trans isomerism, the groups should be on the opposite, the different groups should be on the adjacent carbon atoms. So, here we have the same group on the same carbon atom. So, that means these kind of compounds do not show cis trans isomerism. Similarly, if we have other type of compounds rather than hydrogen, here if there are two methyl groups or any two groups which are similar on any one of the carbon, especially in this particular case on this carbon, that is the terminal carbon, this compound also does not show cis trans isomerism, because if we draw a plane, previously what we saw, we have to draw a plane, and this plane, if the same groups are present on the same side or opposite side. So, here we are only looking at the same carbon atom having same substituent. So, these kind of compounds do not show cis trans isomers. And if we come to the next compound, so here we have four groups which are entirely different. We have hydrogen atom, we have methyl group, we have ethyl group, and we have a propyl group. So, all are different groups. So, in these kind of compounds we can actually have cis trans isomerism. So, if we recollect what we have seen, these type of terminal alkenes do not show cis trans isomerism. Similarly, compounds having Cr2, that means the one of the alkene carbon atom having two same groups also does not show cis trans isomerism, but when 4 groups or atoms are different on the adjacent carbon atom, these kind of compounds show cis trans isomerism. So, this is the thing you have to remember. And when we compare geometric isomers with optical isomers, the geometric isomers have a different reactivity because they have different groups on both the carbon atoms. So, they have different reactivity, but optical isomers, and we will be studying about the enantiomers later on, they react at the same rate. If it is enantiomers, they react at same rate. If it is diastereomer, they react at different rates. So, there is a difference between enantiomer and diastereomer. Diastereomer react at different rate, but when it is an enantiomer, they both react at the same rate. And the geometric isomers generally have different physical properties. That means, we have cis and trans isomers. So, we will see about some of the properties of few compounds and how the physical properties are different, we will see. Optical isomers, basically enantiomers will have same physical properties, and the geometric isomers are generally optically inactive, whereas optical isomers are optically active. In the next session, we will study more about what is optical activity and optical isomerism. So, when we talk about stereoisomers, we will once again reiterate the atoms or groups in a molecule can have different arrangements in space. So, this is the most important thing. The spatial orientations are different in stereoisomerism. So, let us look at some of the physical property difference between cis trans isomer. We have a cis isomer, we have a trans isomer. So, here the cis isomer is a dicarboxylic acid, that is a maleic acid. So, this is having a melting point 135, whereas fumaric acid is having a melting point, very high melting point 286. And if you look at the boiling point, the cis isomer boils at 160 degree centigrade, whereas the trans isomer boils or sublimes at 200 degree centigrade. And this cis isomer is actually not present in nature, whereas the trans isomer is present abundant in nature. And this can form a intramolecular hydrogen bonding. So, that means within this molecule itself, it can form a intramolecular hydrogen bonding. Whereas, in the trans isomer, these two groups, that hydrogens are far away from each other. So, they actually form intermolecular, that means with another molecule of the trans isomer, it can form hydrogen bonding. So, this is how cis and trans isomers have different physical and chemical properties also. Let us do a small comparison between cis and trans isomers. As we have seen, what are cis isomers? Cis isomers will have similar groups on the same side across the double bond, whereas in the trans case, similar groups are present in the opposite side across the double bond. And when we talk about cis isomers, these are all the most polar molecule. We will see an example soon. And in the case of trans isomers, they are actually non-polar or less polar molecules. As we have seen in the previous slide, the cis isomers are having high boiling point due to the strong attractive forces, and the trans isomers have low boiling point due to weak attractive forces. And cis isomers are less symmetrical or loosely packed, so they have low melting point, whereas the trans isomers are symmetrical or tightly packed, so they have high melting points. And cis isomers have high solubility in inert solvents, whereas trans isomers are less soluble in inert solvents.